you started the homework already.
I mean, I don't know anything, but
I see. Good. Oh, did you do 61B last semester or something?
No, I did.
Okay. All right. Let's see. What's the first word on my slide? Woohoo! Okay, sorry. Sorry. I love proofs. Do you love proofs? Who loves proofs? Okay, yeah. You should love proofs. Otherwise, you don't know whether the stuff's working, right? So, propositional logic identities. I just wanted to review them real quick. These are identities we just proved or argued last lecture. So these are De Morgan's sort of laws. What happens when you negate an expression? You can carry it in and follow various rules for all. You can put a negation across it, and you get it there exist. That's syntactically, but you should also understand if something doesn't hold for everything, there must be a counterexample. So it's actually a very nice thing that we use in proofs. Either prove or give a counterexample. So that that's proving whether the statement is true or false. Okay, so there's more De Morgan's laws. These are the same ones, but they were meant to be different. Okay, so these two expressions here, P implies Q, is equivalent to not Q. It's not equivalent to not. It should be not Q implies not P. I'll fix that. P implies Q is equivalent to not P or Q, right? Because it says if P is true, the not P here will become a false, right? And then if that's false, then Q better be true. Does that make sense? Okay. So P implies Q. P is the antecedent of this implication. I might use the word antecedent. I just don't want you to get confused or assumption. And Q is a consequent or conclusion. So, and here's this puzzle. I don't know, you turn over some of these cards, right? On one side it has their age, on the other side it has their beverage. And one of these beverages is alcoholic and one is not. So you want to test this theory. Which cards do you need to turn over and see the other quantity, right? I don't know. I could guess. I could try to think about it in my head. But instead, what I did is I write the two implications. I write drink implies greater than 18, and then I write less than 18 is don't drink. I wrote the implication and it's contrapositive. And now I can just look at the left-hand sides and say, okay, drink. This one says drink. This one says the soda is not drink, so I don't need to worry about it, right? And so I don't need to turn that on. Drink, I better check whether the person's over 18. For this one, this guy's bigger than 25, so this particular implication is about age, the left-hand side, the antecedent, and you can just apply it, and you say, oh, the 16-year-old, I better check their ID, right? Okay, does that make sense? And see if they're drinking. So, and that just tests the theory. I think this theory is probably false. Maybe not for these cards. Okay? It's easier just to do it mechanically sometimes for these things. So today we're going to do proofs. We're going to do one by example. A direct proof is prove that P implies Q. You have these if-then statements. We saw some of these. If A is greater than B is greater than or equal to C, then and they're the side lengths of a right triangle, then A squared plus B squared is equal to C squared. Okay? So that's the condition P was if A, the right triangle and A is greater than B is greater than C. Okay, contraposition is you want to prove the statement P implies Q, and somehow it's easier to prove the statement not Q implies P. Contradiction, we'll get into that in detail, but what we do is we assume that the statement is false, and then we prove something false. Okay? So if false implies false, what is the contraposition of that? True implies true. So that's how you prove the original statement is true. But I'll get into more details later. By cases, we'll split it. We already saw proof by cases where we simplified the formula for distributive, the distributive formula of ands over ors. What we did is we assumed the first proposition was true and proved that the equivalence in that case, and then we proved it in the false case too. So we'll do more examples of that. Okay, so some background. When we prove something, we usually work with certain kinds of objects. It's good to understand their basic properties and the basic definitions about how they are, so it's precise and you can work with them efficiently. So B is in the integer, so is A plus B. So this is just something we know that if you add two integers, it's an integer. Okay, so we're going to assume that. This little notation here, this vertical bar, B, means A divides B. Okay? And that's just words. So, what, is this true or false? It's a statement. Is this true or false? Yeah. How about this one? No, it doesn't divide B. Okay, no, yes, no, yes. Does 4 divide 2? Does 4 divide 2? What do we think? Yeah, no. But this is why it doesn't. Okay, so now I make it more formal. You were slightly confused as to whether, okay, it's sort of a multiple of 2. But specifically what we mean when A divides B is there exists some integer Q where B equals AQ. And this is very convenient to have a formula now, right? You have just an equality there, and now you can work with this equality, and you'll see that over and over again. Okay, so instead of using the words, it's just a very precise definition here. There exists a Q in the integers where B equals A times Q. So does 3 divide 15? So instead of guessing, we say, we illustrate the Q, right? And there exists a statement, we just need to find some Q where this equation is satisfied. Okay, so there exists a Q in the integers, so we're going to pick 5, where 15 B equals A times 5. Okay? I mean, this is a little boring, but, and these are why these are all true. Okay? So in particular, the reason 4 doesn't divide 2 is 4 is bigger than 2. Any integer times 4 will be bigger than 2 in absolute value. So it will never equal 2. Okay? A natural number p greater than 1 is prime if it is divisible only by 1 in itself. Okay, so those are the definitions we're going to use. We're going to now prove some theorems using those concepts. Okay, for any a, b, and c and z in the integers, if a divides b and a divides c, then a divides b minus c. It divides a difference, right? Okay, so we're going to do a direct proof here. So what we're doing is we're assuming, okay, I thought that would turn blue. Sorry. Okay, so we're going to assume that the P part of the statement is A divides B and A divides C, so we're going to assume that. And what we're going to say is there exists some Q where B equals A times Q. So now we have an equality, right? So that's nice to work with, right? It's not sort of going to be waving our hands. It's very precise now, okay? And we know that there's some integer Q where C equals A times Q, okay? And once you do that, it becomes a triviality, right? Then you write down the expression over there, B minus C, and you get B minus C, and then you write down the other sides of the equalities here, AQ minus AQ prime, because AQ is B and AQ prime is C, and you factor. And now what do you see? You see that, are you done now? What do we want to show? We want to show that A divides B minus C. So that's what we want to say is there's some integer times A that equals B minus C. Okay, so we get something here times A, and that equals B minus C. Now what is that something? It's Q minus Q prime. Now q is an integer and q prime is an integer. Is that so? Is q minus q prime an integer? Okay. So A divides BC. So we use the definition twice. We use the definition to translate the first expressions into something equalities, and then we worked with those equalities, and then we use the definition to translate it from the equality that we got here in this third or fourth line back to the definition. Okay. Okay. So now this argument we sort of started after the for all with the argument. Okay. We just started with the A, B, and C, right? Any A, B, and C. But the argument works for any A, B, and C in the integers. Okay, so what we've done is we we proved it for all A, B, and C. There's nothing in this argument that was specific to the choice of A, B, and C, since they were variables that were our only assumption about them was they were integers. Okay, so the form of this proof was. We had this statement, and we want this statement to hold for all integers, but we have this P implies Q, right? That was the statement. And what we did is we assumed P, which is this first assumption. We assumed the P part of our statement, and then we did a bunch of arguments based on what that meant, right? We translated the assumption into a different form, essentially, and that form turned out to be a Q. Okay, and so that's what we did. Okay, using rules that all work, right? Rules of arithmetic that we all know. Okay, so now that's one direct proof. So here, let's try another one. But I think it's nice to know, right? We really, even for such a simple thing, we name things carefully. We translated into equalities. We did step by step where the steps made sense, right? We're clear. Okay. Later in the course, we're less detailed, but in a sense, that process is still happening. Okay. That precision is happening, and that's one of the challenges in this course is that. The proofs will look almost the same, but one is just completely correct and one isn't because the precision is not there, right? You're just sort of skipping steps or waving your hands a little bit, even though many of the steps look the same. Okay. So so D3 are all the three-digit natural numbers, right? 100 through 999. Does that make sense? 101 is a three-digit natural number, and so on, in page 10. Okay. So we want to prove that if the alternating sum of digits of n is divisible by 11, then 11 divides n. Okay? Does that make sense? Okay, so let's give you an example. So here's a three-digit number. It's in D3. If we add its alternating sum, 1 minus 2 plus 1, you get 0. Is 0 divisible by 11? Yeah, so I guess I lied in the previous slide. If it's 0 is divisible by everything, right? Because you can multiply anything by 0 and get 0. Okay? There is a q that you can multiply 11 by to get 0. The q is 0. Okay. And 121 is also divisible by 11, right? 121 is 11 squared. Okay, 605. 6 minus 0 plus 5 is 11, so it's divisible by 11. And 605 is divisible by 11. Is that easy to see? 11 times 600? Yeah, no. 11 times 60? What is that? I don't know. It's divisible by 11. So, 55. There it is. Okay. Okay, so now let's prove this theorem. For n and D3, okay, this is the miracle, right? Remember these things? This is the place value, right? Your teacher told what's the ones place is C. We think of, if it's three digits, we think of C as the 1 in the n equals 121, and B as the 2, and A as the 1. But the 1 in the A's place really means how many hundreds you have, right? It's the miracle of place values. Yeah, it's a beautiful thing, actually. So Now we can take the alternating sum of digits when we write it this way. We have some number n which has a value, and we have its representation as ABC, as the digits A, B, and C. And so the alternating sum is just A minus B plus C. Okay? And what is our assumption about this alternating sum? That equals this alternating sum is divisible by 11. So 11 times some integer is equal to A minus B plus C. Okay. So this is like, okay, so now what I want to do is I want to get Q somehow. 11 divides N, right? And now we see N up here. And we see the left-hand side, which kind of looks like N, but it doesn't. How might we change it to look like N? Well, if you want to change one number, yeah. Yeah. Right. So what he said is that if you have two integers and you want to change one into the other, you add the difference. Right? So in some sense, this just seems arbitrary. Okay, what did I just do? I did it because, I know what I'm trying to get. I'm trying to get N on the left-hand side somewhere. Okay? And I got something that looks like it could go to N, I don't know. But, you can make any integer the same by adding the difference, right? Okay, so I added a difference, which is what he said. It's 99A plus 11B. Okay? So 99A plus 11B gives you, 100 A's, 11 B's minus 1B for the negative here. And you get a 10B in the middle, and then you get the C was there first. Okay, now on the other side, we get 11K plus 99A plus 11B. Okay, so this is N, and we wanted to say N was divisible by 11. And there's something very nice about the right-hand side here. Do you see it? Can I factor 11 out of just the coefficients here? Okay. So now the final step is, what do we need to say about K plus 9A plus B? It's an integer, right? And then we've proven our statement that 11 divides N. Okay? Does that make sense? Okay. Okay, so that's the direct proof of P implies Q. So P, again, is the assumption that 11 divides. We started with this statement. 11 divides A minus B plus C. We translated it into an equation. We did some manipulation, and we got an equation. We translated it back to the statement. Okay. For all N and D3, now what is this? Is this the same statement as we'd had before? No, it tells you what it is up at the top. It's the converse, right? We switched to P and Q. Okay. Is the converse a theorem? Is it true? We had, right, this is a converse. It's not always a theorem. If we want to prove this, we actually have to do a proof. It's not the contrapositive. Okay. So who thinks it's a theorem? Is this true or is it false? I don't know. It's true. I wrote theorem next to it, so I hope it's true. But okay, why? In some sense, in this case, the proof is basically the same. So you start with 11 divides N, right? So you start with N, and then you rewrite it as these digits, right? Because we're targeting something about the digits. So we write N as its digits in the form that from the digits, 100 times the place value for hundreds, and so on. Okay, and that equals 11K, right? N equals some multiple of 11, some integer multiple where K is an integer. Okay? Now what should we do? What did we do last time? We want to get eventually the alternating sum, right? That's what Q is saying. Something about the alternating sum. So how might we change the left-hand side here of this equation into the alternating sum? Well, we just subtract until we get the same form again. Okay? So, or what we did is we didn't subtract. We just pulled out, right? We pulled out the alternating sum out of there, and we wrote it this way. Okay? Does that make sense? How many A's are on the left-hand side? It's 99 A's plus 1A. So that's 100. How many b's? 11b minus b plus c. So we're not going to subtract on that side yet. Now we subtract. Okay? Okay, so I just did it in 2 steps. Okay, so now you have the alternating sum on the left, and what's you want to say the thing on the left, that's what you're trying to prove, that this alternating sum of digits of n is divisible by 11, or is some multiple of 11. And again, the right-hand side, you see something nice about it, right? What can you do? Yeah, and so on. And then you're done. Right? Which is in the integers. So that is 11 divides the alternating sum of digits. The alternating sum of digits is the left-hand side of this equation, a minus b plus c, and it's equal to 11 times some integer l. Okay. Okay, in some sense, this looks the same. It's the same idea. Okay? And that's because basically every step in the previous proof was not just an implication, it was if and only if. It's only true that 100a plus 10b plus c is equal to 11k if and only if the second statement is true. Right? So if you know the second statement, the first statement is true. Right? You can go either way. So in this case, the whole proof actually works in both directions, and it is the same proof. Okay. It often works with arithmetic properties, except for there are some dangers here. When you multiply an equation, both sides of an equation, it still remains an equation, right? Say you have 3 equals 3. If you multiply both sides by 0, what do you get? 0 equals 0. So that's good. It's still true that if you multiply both sides by 0, you're good. And that's what we're using, right? We're using if you multiply both sides by an integer, you get an equation that satisfies. We're not using that here. We don't need that here. We're adding. We're not multiplying. So, but on the other hand, let's say I take the equation, the equation, 3 equals 4. Okay? That's not right. It's not right? Now you multiply both sides by 0, what do you get? 0 equals 0. So it doesn't mean because after you multiply by 0, you get an equation that's satisfied. It doesn't mean the equation before was satisfied. Does that make sense? Okay, so that's kind of 0 is a magic thing, and we'll use it a lot to do really magical things. Look, if we grade your thing and we say this equation is wrong, 3 equals 4, you can say, I'm just going to multiply both sides by 0. Now the equation is right. Give me my points. Right? That's magic. Right? It's like an error correction thing, and we will use this property exactly in error correction. We will show you error correction algorithms that do this. So it's kind of an amazing thing. Anyway, that was an aside. Okay, so now we have this theorem in both directions. Okay, that's direct proofs. That's a direct proof. Okay, so now let's say n is in the positive integers, and d divides n, and n is odd. Then d is odd. Let's try to prove this theorem. Okay? What does it mean to be odd? Here I didn't give you the definition up front, but what it means is that n equals 2k plus 1 for some natural number, or some integer. Okay? That's a definition of odd. Okay? So n is odd, right? We're starting with the assumption we're going to write an equality. Okay, what do we know about d? What do we do now? Is it even true? What to do? Is it even true? It rhymes. And there's even a pun. Okay, so, okay. Color blue. I don't know who put that in my slides. Sorry. But what do we do? Yeah, well, okay, n is a multiple of d. There's some integer of a times d, which equals 2k plus 1. What do we do now? It's like, oh, what a mess. Okay? Well, our goal is to prove p implies q. N is odd should imply that d is odd, right? That's our goal. Okay? Remember, it's the same statement. P implies Q is the same as not Q implies P, not P. Which is equivalent, right? These are the same statements, right? So, let's try to prove it in this form. What is not Q now, and prove not P. That's what we're going to do, okay? So, in this case, not Q, what is Q? Q is D is odd. What is the negation of that? It's D is even, right? So the definition of D is even is D equals 2K. We know that D divides N as well. We're also given that, right? That's given before. So we know that N equals some integer Q times D, right? And now what can we do with D? We have an equality here, D equals 2K. So we can replace D by 2K, right? Which is what we'll do. And then we see that 2 times N is equal to 2 times KQ. Right? It's a triviality. You don't need to write poems about how hard it is, or bad poetry about how hard it is. It's easy, right? If you just do it by contrapositive. Okay? So N is even, right? Because now N is a multiple of 2. Okay. Which is not P. So again, we started this text with not Q with our assumption. We did some argument in the middle. And we have obtained a statement which was not P. So not Q implied not P. Okay. So how about another contradiction? Okay, so this one, for every n in n squared is even, implies that n is even. Okay? Okay. So here too you have the problem. We can start this way. We can start with P and try working with it. And we get that n squared is equal to 2 times k. Now we're asking whether square root 2k is even, right? It's not even clear that square root 2k is an integer, except we know that here and it is, but it wouldn't be, except for we know it's n squared. So now it's, again, hard to reason in this direction, right? It's unclear what to do. Okay, so let's do it by contraposition. What is a contraposition? Is not Q implies not P. What is not Q? Remember, Q is n is even. So what is not Q? N is odd, right? So here P is n squared is even, and not P is n squared is odd. Q is n is even, and not Q is n is odd. So we just translate it all over. So now we start with n is odd, and we want to prove that n squared is odd. And that's a triviality, right? It's almost a triviality. I'll do it, but it's just basically, let's do it. So n is, we write it down as n equals 2k plus 1. It's still not a triviality in words, but once you translate it to what does odd mean as an equality, then it becomes very easy. N equals 2k. You obviously square both sides to get n squared on one side. And you know how to square, so this is how you square. And now, here you notice that you can factor 2 out of the first 2 terms, which is what's happening here. And now we have n squared is equal to 2 times L plus 1, where L is this 2k squared plus 2k. And 2k squared plus 2k is an integer, is a natural number even, right? Okay, so therefore, now we know n squared is 2L plus 1. That's the definition of odd. Okay? So again, it can be way more convenient to start one way than the other way. Okay? Okay, so now we're going to do this notion of proof by contradiction. Now, square root 2 is irrational. Okay, so at first it seems this is where it's kind of mysterious how you would do this, right? Because what I want to show that for every A, B, and C, every one, that A over B squared is not equal to 2, right? You see why that seems like it might be hard? Here's a lot of them, right? There's a lot of A's and B's here, right? And in fact, you can sort of get closer and closer, if you use big enough A's and B's, right? But it's, it's like, how do I show for every pair they don't equal this, right? So, yeah, in this case, when we want to show something that doesn't exist, one way to deal with it is just try to show it does exist and say, that's nonsense, it can't exist. Okay, that's what contradiction is. Okay? If you try to show this thing in these proofs that you're trying to show, particularly something that doesn't exist, one way to do that is show it does exist. Assume it does exist and prove something ridiculous. So, it's a simple property. This equality should not always not hold. Okay, that's what we want. So proof by contradiction is we have this theorem P that we're trying to prove, that square root 2 is irrational. So we're going to assume the opposite, and then we're going to do some proof. Somewhere in there we're going to make some statement. Okay, some weird statement, R. Okay, from starting with P, not P, we're going to prove R. And then starting from not P, we're going to prove not R. Okay? And the key is, so not P implies both R and it implies not R. So this expression, R and not R, what is that? It's false. So not P implied false. Okay? So not P implies false. What is the contrapositive of this statement? That not P implies false. The contrapositive of not P implies false is true implies P. Right? It says that P is true. Right? So if you use not P to prove something ridiculous, then you know it can't be true that P is false. Okay, so this is what you want to do. You're starting with nothing. True is just nothing, no statement, right? It's just, and then you're saying P is true. Okay, that's the proof. That's the proof technique. That's a sort of blow by blow, play by play of so far nothing. But it's the format. Okay, so we're going to assume not P. Okay. What's the opposite of irrational is rational. What rational means is that there are integers a and b where a over b equals square root 2. Okay? Okay, so now we have an equality, and what we can do, we can manipulate it, right? Well, almost the obvious thing here is that, well, I don't like square roots, let's just get rid of them. How do we get rid of this square root on one side? Okay, well, we're going to assume one more thing, that a and b have no common factors. First, we're going to make, it's going to be important for the proof, sorry. A over b, and we're going to assume they have no common factors. Does that make sense? Okay, so it's in reduced form. Okay, so we have this root 2b equals a, we get rid of the fractions, then we square both sides, we get 2b squared equals a squared. We know a squared is even. So what do we know about a? It's even. We just proved it, right? We proved that if n squared is odd, then it's odd, and so on. Okay? Okay, so a is 2k for some integer. That's what it means for it to be even, right? Okay, so let's plug in 2k for a, and what we get is 2b squared equals 4k squared, right? Does that make sense? All I did is, I said a is even, because a squared is even. Why is a squared even? Because there's a 2 in front of the b squared, and b squared is an integer. A squared is even implies that a is even, so there a equals 2k. I'm plugging in 2k, and I get a 4k squared. Okay, so now I'm copying that down. I divide. I divide it by 2, right? Both sides of the equation. 2b squared equals 4k squared. I divide both sides by 2. I get b squared equals 2k squared. What do I know about b now? B is even, right? Because b squared is even, therefore b is even, right? B squared is even, therefore b is even, right? Okay, do we see a contradiction here? A and B have a common factor, right? What is the common factor? 2. So I proved, here I could just assume A and B have no common factors, and they also proved that they have common factors. Okay? So these statements are contradictions of each other. So from this proof, I produced 2 statements that are contradictions of each other. I mean, I could have just said that contradiction is you start with the negation of the theorem and you prove false. But in fact, what always seems to happen is you get these 2 red lines. You have one thing and you have another thing, and that's really where you see that it's false, right? You assume that A and B have no common factors. You did nothing else wrong. You assumed that root 2 had the form A over B. You assumed that A over B had no common factors, which is perfectly fine. And then you prove that A and B have common factors. Okay? So it says you can't have such an A and B. Okay? Other questions? Yeah. We just reduce it if it isn't. If you have an A and B, where A over B equals root 2, you can take out the common factors and divide them out. Does that make sense? Right? You're saying, look, I could write 2/3 as 4/6, right? I could write 2/3 as, but I could also take 4/6 and reduce it to 2/3. Right? That's all I'm saying. If there's an even number over an even number, I can divide out 2 out of both of them. So I could divide it until at least they're both odd, right? I mean, even if I don't want to get rid of all common factors, I could just get rid of all factors of 2, if that's easier to think about. He asked, why can I assume they have no common factors? Technically, there's a bit of an issue with that, and we'll talk about it, but this is what I'm saying. This is where we're going. Okay, there are infinitely many primes. Okay, that's a theorem. Okay, again, it's one of these theorems that says, I just have an infinite number of them. And this is, one way to show this is generate them. I can maybe generate a lot of primes. I can show you, here's how you make a prime. And here's how to make another prime. And here's how to make something that keeps generating primes. That would be nice. But actually generating primes is a real challenge. It's hard to do, actually. So this is, it's way, way beyond this class, and I'm not even sure it can be done. Okay? But I give you so how else would you show there's an infinitely many number of primes? How else might you do it? Well, it's going to be by contradiction, so we're going to say, let's assume there's only a few. Now we have something concrete to work with. We have this P1 through Pk. We assume not a few, but maybe there's many, but there's a finite number. There's just not an infinite number. If it's not infinite, I can write them all down. Okay? I can write them down in some list, P1 through Pk. Okay? This is all the primes. That's what I'm assuming. So again, I'm assuming the contradiction of the theorem that says there's infinitely many primes. I'm going to assume the negation, which is that I assume there's finitely many primes. Now I'm going to consider a number. Okay? This number. And multiply all my primes together and add 1. Okay? That's just some number q. Now, there's a question. Is q prime or not? Now we're going to say, we're talking about primes. Let's going to examine whether q could be prime or not. Okay? Okay, it can't be primed, right? Because we assume there's only a finitely many number of them. And the answer is no. It can't be one of the primes, as it's larger than all of the primes. We multiplied them all together and added 1. So it's bigger than all the primes. Okay? And all the primes are greater than 1 anyway. So even without adding 1, it's larger than all the primes. Okay? So it can't be prime, given the reasoning in this proof. So Q has to have a prime divisor. If it's not prime, there must be a divisor that's bigger than 1 that divides it. Right? So there must be some prime, but divisor P bigger than 1, which divides it. And I'm putting quotes and saying that's a statement R. So there's some prime p which is larger than 1 that divides q. Okay? And moreover, if it's a prime divisor, if it's a prime, it must be one of these primes, because that's all the primes. So it's one of these pi's. Okay? So P has to divide this term, P1 times P2 up to Pk. Why? Why does it have to divide X? Because it's one of those numbers. Right? P is one of these PIs. So if it's one of these PIs, it divides, you just multiply all the other PIs together, PJs together. Okay? So you know that P divides X. Okay? So P divides Q. That's from the statement up here. And P divides X. So if it divides P and if it divides Q and it divides X, then the very first thing we proved is that it divides X minus Q, or Q. It should say Q minus X, but okay, it divides Q minus X or X minus Q, but it divides Q minus X. Okay. Okay. So we know that P divides Q minus X. It doesn't matter. This works the way I define divides, but because you could use -1, but still. So P must be smaller in absolute value than X minus Q. Right? What is X minus? It should be Q minus X. I apologize. It should be 1. Is 1. Right? If you put Q minus X, Q is X plus 1. Okay? Okay, so that tells us that if P divides Q minus X, P must be less than 1. Okay? Over there, we said P is greater than 1. So these are contradictions, right? So that tells us that the original statement that there's finitely many primes is false. If there's not finitely many primes, there must be infinitely many primes. Yeah. He's saying, yeah, good question. Okay, he's asking this question. Did we just prove this? Did we prove the product of the first k primes plus 1 is prime? Right? Because in the context of that proof, he said, oh, yeah, Q must be prime then. Otherwise, that doesn't make sense, right? But we assume something false in the first place, in the middle. Okay? So let's look at this. So the question is, at the beginning, before I even started, I said it's hard to generate primes, and here's something that seemingly generated a prime. Good question, right? Because I multiplied together the first k primes and add 1, it's prime, right? If it wasn't prime, there's some contradiction. But the thing is, this is only in the context of that proof, right? So the chain of reasoning started with a false statement. So anything you say in the middle is kind of suspect. Okay, and in fact, it's just false. The statement is false. You can multiply together the first 6 primes and add 1, and that's not prime. So the thing is, the reason, the specific detailed place where the argument fails is it's not the first k primes. We said there's no primes anywhere else. So now we're saying there's a prime between the first k and the number you have. Right? That's the specific spot where it fails. Right. Yeah, I mean, you got to be a little careful about thinking too hard about statements you make in the middle of these contradiction proofs, because you started with something false. So there's a lot of nonsense that happens at some point. But yeah, and in particular, the particular place here is it's true that none of these primes divide x plus 1. That all works, but there's other primes that can't. So therefore, it's not prime. Yeah. Yeah.
So, like from the last proof, why does P have to be a prime divisor? Why can't it just be like
Well, if it has a divisor, you might as well use a prime. It also has a prime divisor, right? So you just keep taking primes until You keep taking divisors until you find a prime divisor. That's a good question, too. He asked, why does P on this equation? I said, Q has a prime divisor. So I sort of maybe skipped an argument that says Q has a divisor. But if it has a divisor, we keep going until we get a prime divisor. Because the divisor of a divisor is still a divisor. It's sort of the same thing as factoring out the 2's, reducing the form. Okay, so, yeah. Okay, so there's another, let's give you a break. I'll give you a break, yeah. Why don't you take a break for a couple of minutes? Okay. Okay, so we're gonna prove this theorem by cases. Okay, so first we're gonna prove a lemma. Okay, so if x, the lemma is gonna be proven by cases. If x is a solution to x to the fifth minus x plus 1 equals 0, and x equals a over b equals for a over b and z, then both a and b are even. So this should be a little familiar, right? This is sort of what we were saying. It's sort of like the lemma you could think of what we said, a over root 2 is irrational, is saying that x squared equals 1 has no solution in the rationals. Okay? That's what we prove it for. X squared equals 1 has no solution in the rationals. So now we're proving some other equation has no solution in the rationals. Okay? Does that make sense? Okay. So it's going to have a similar flavor to what we did with root 2, showing root 2 is irrational. Okay, so if x is a solution to this equation and it's in the rationals, we go ahead and assume there is some solution, a and b. Then we're going to show both a and b are even. Okay, it's so again, we're going to use, and then from this lemma, we're done because we could then use this reduced form again. We could just take out all factors of 2, and then we still have a solution in the rationals where there's no factors of 2, which contradicts the lemma, which says only a and b must be even. Okay. Okay, so let's assume a solution of a over b, and now it's nice. Once we assume a over b, we assume that the lemma allows us, that it's actually writing out, in some sense, the main engine of the contradiction. So we assume a solution of the form a over b. And we plug it into our equation, right? That's the obvious thing to do. We get rid of all those fractions, and we get this equation. Okay. So now we have all these things about when we multiply two odds, you get an odd. When you multiply two evens, you get an even. When you multiply an even by an odd, you get an even. When you multiply that's it. That's all the case. Even by even, you get an even. Right? Okay, so let's look at those cases. Odds are here. We have a to the fifth. It's odd. Any multiple, all these things are odds. So there's no factors of 2 in a to the fifth. So that's odd. There's no factors of 2 in times b to the fourth. So that's odd. There's no factors of 2 in b to the fifth. So that's odd. So you get odd minus odd plus odd is equal to even. 0 is even. Is that possible? What would odd minus odd plus odd be? Yeah, it's odd, right? You just think of it as it's an even plus 1, an even plus 1, an even plus 1, and then you're going to have 3, the 1 minus 1 plus 1. You'll still have a plus 1, an even plus 1. Okay? Okay, so A is even and B is odd. You look at the first term, it's even. The second term, it's even, and it has a factor of 2. The third term does not. And yet it equals even. An even minus an even plus an odd is even, is not possible. And this, again, is not possible. If it's even, then you have a to the fifth is even, a times b to the fourth is even, plus b to the fifth is even. So that one's possible. So we haven't eliminated all the possibilities, but that's all the theorem asks for. The fourth case is the only one possible, and that's what the lemma says. Both a and b are even. Okay? So it's just we're sort of working out the cases and say, oh, look, in every one of these cases it doesn't happen, so therefore the only case where it could happen is a and b are even, and then that's all the lemma is asking you to prove. And then we use the lemma to then conclude there's no rational solution using a reduced form. Okay, so here's another proof by cases. There exists an irrational x and y such that x to the y is rational. Okay. Okay, so this seems nice, right? It seems really nice. Here, it just says there exists. All I need to do is show you an example. Okay? I'm going to show you something, but it's going to be slightly unsatisfying. I'm not going to give you an example. I'm going to show you some possibilities, and tell you one of them is true. Okay? Okay. So this is a math thing. Yeah, those math people, I don't know. I'd rather just show you the pair that works, but unfortunately I can't do that. So let's say x equals y equals root 2. Let's just pick one, right? Because we know what number do we know is irrational? Root 2. Might as well try that. Okay, that's the one number so far that we've figured out is irrational. So there are two irrational numbers, x and y, and both of them happen to be root 2. Okay? So now what do? We say, well, let's look at x to the y. Now there's two cases. It's either rational or it isn't rational. Okay? So let's look at the first case where x to the y, which is root 2 to the root 2, right? Let's say it's rational. Okay? Are we done? In this case, does the theorem hold? Right. But maybe x to the y is not rational, right? Maybe it's irrational. Okay, that one, in this case, we're done, right? So now, root 2 to the root 2 is irrational now. Let's assume that. It could be, we don't know what it is. I'm making no claims about that I know whether it's rational or not. I have no idea. But it's one of the two. So in the case it is rational, we're done. The theorem is proven. In the other case, we're going to assume that root 2 to the root 2 is irrational. Okay, so now I have another irrational number, right? I got two of them. I got root 2 and I got a root 2 to the root 2 in this case, in this world. Okay? So let me try those two as x and y. Let's let x be root 2 to the root 2 and y be root 2. Okay, so just for a second, do the next step yourself. What am I going to do next? I'm going to look at x to the y. Oh, you see? You see what happens? Okay. So you get x to the y. What's my next step? What do I do with these exponents here? There's an exponent root 2 and another exponent root 2. What do they do? Right? Oh my. Is 2 rational? 2 is rational. Right? Thus, we have an irrational x and y with a rational x to the y, in this case, right? And another case. So one of the cases is true. We don't know which one. I don't know which. I haven't given you an example. I say one of these two examples works, which is better usually than math. Math just says there exists an example somewhere and they tell you nothing about it. But this one, at least, not always, but sometimes. But this one of these two things actually hold for the theorem. Okay? We don't know which one. Is that clear? Okay. I see. Which case holds? I have no idea. All right. So we can prove more theorems, right? So let's prove this theorem: 3 equals 4. It's going to be you can assume 3 equals 4. You start with 12 equals 12. You divide both sides by one side by 3 because those two are equal, so you can divide both sides by the expression from the equality, and then the other side by 4, and we get 4 equals 3. It's commutative, right? Equality is commutative. Yeah, so you got to be careful. So what did they do wrong? You don't want to assume what you want to prove, right? Like I assume something false and I prove something false. I could pretty much prove anything if I start with something false, right? Does that make sense? Okay, so you got to be a little careful. And it's sometimes it happens like on accident. You reformulate what you're trying to prove in some sort of way that's just syntactic. And then you prove it, and then the grader says you assumed what you wanted to prove. So you got to be careful. Yeah.
In the last example, when we're using our new x of rad 2 to the rad 2, doesn't the original theorem state that it has to be an irrational x?
Oh, okay, yeah. He just wants. Okay, so maybe I didn't fill out the steps. So here in this world, in case 2, the original theorem says both x and y are irrational. We know y is irrational because we proved that before. And we need to show that x is irrational. But we're not showing it's irrational. We're just saying it. In this case, it's irrational. Right? Yeah, this case is irrational. It may or may not be irrational. But if it's rational, we're done from the first case. What he said is, like really, this root 2 to the root 2 might be rational. So this whole case 2 is nonsense then. It makes no sense. But we just don't know which one of these which one of these cases hold. One of them holds. Either case, the theorem holds. Okay, so this theorem doesn't hold. Okay. This is for x equals y. Sure, why not, right? Is that true? I'm just starting with some x and some y. We all believe this, right? Because if you place you got x squared minus xy, but if you replace that with x squared minus yy or y squared, you get the same thing on the left-hand side and the right-hand side. And what is the thing on the right-hand side? I always told my kids, the one thing you have to always remember is difference of squares, right? Yeah, math people love difference of squares, and it's really beautiful. It's a beautiful thing. If you go on, and all of a sudden, that's because of difference of squares, deep in your research career. But this is a difference of squares, and I guess that was not. Right? So you can factor out. Right? Well, there's a common factor, right? X minus y and x minus y. Seems fine. Y equals x, right? You should be happier when I prove things are correct, right? Yeah, okay, well, what's the problem here? Yeah, let's get a different. Yeah. Okay. What we did here, we did actually what I said before, right? In this case, it's all good until this place, but then if x equals y, you have 0 and 0, and that's fine. That equation is satisfied, right? Yes. And then it is, right? 0 equals 0 is an equation that's satisfied, right? I mean, in fact, you started with 0 equals 0, right? And then you divided out 0 and made up numbers, and that, the other way works, but it doesn't work in that direction. Okay? In that case, if you multiply an equation by any integer, both sides by the same number, it's true the equation will still be satisfied. But it doesn't mean the reverse doesn't work, right? So multiplying both sides of an equation by 0 does keep it an equation, but in fact, multiplying both sides of a wrong equation by 0 makes it right. And we're going to use exactly this fact in error correction. It's going to be like shocking and amazing, but that's later. But yeah, you got to be careful with 0. And multiplying inequalities by a negative, that's also a problem. It switches the directionality. So these are other arithmetic mistakes. Okay? So this is a summary of note 2, and then we'll do some induction. Okay, so you want to prove P implies Q, assume P, then prove Q. By contraposition, you try to prove P implies Q, it's not working for you, so just switch it around, right? Assume not Q and prove not P. See if that works better. Just play around with it. Okay, by contradiction, to prove P, you assume not P, and then you prove false. But in general, the way false comes about is you prove a statement, and then you prove the opposite of that same statement, and that's how false comes about. It's just a little bit slower way of saying the same thing. Okay, by cases, it's you want to show the statement holds in all cases if it's universal, right? If you want to show no matter what, right, with the x to the 5th minus x plus 1, for all the cases we had to examine them, and they had to either not be true for the 3 cases or be true in the last case, and that was fine when both were even. But in existence, we said, okay, one of these 2 cases hold. We don't know which one, but all we're trying to show is existence, and one of these cases the thing exists. Okay? The cases are either root 2 and root 2 are rational, and the root 2 to the root 2 is rational, or root 2 and root 2 to the root 2 is irrational, and we know that root 2 to the root 2 to the root 2 is rational, is 2. Okay, and you should be careful when you're proving things, right? You don't want to prove 1 equals 2. That'll look bad. So, although you seem to find it amusing. And you don't assume the theorem, and be careful about dividing by 0. Converse is not true because the implication is true. Those are all things. Okay, so let's go to the next note, which is induction. Okay, so what are the natural numbers? Okay, so there's this ladder. So the natural number is 1, and then what the natural numbers literally are is there's the next one. There's the first one, 0, and there's always the next one, right? After 1, do you all know the next one? 2. Yeah, it's not too hard, right? 3. Okay. At some point, you're at n. After n, is there a next one? Yeah. Okay, that's the thing about the natural numbers. I know the biggest number. No, I know your number plus 1, right? No one wins this game. I mean, or everybody wins the game. It's entertaining for a while. Okay, so that's what the natural numbers are. There's a number. There's a next one. There's a next one. There's a next one, and it goes on forever. Okay. Okay, so hello, class. Okay, who wants to do that? Well, you probably all know the formula, but Gauss was only 5 years old, and he just said it was 50-50. So, okay, this is what he did when he was 5. I don't know whether it's true. We tell the story. He's all the other things the man has done. It's totally believable. So what the 5-year-old Gauss did is he proved this theorem. He proved a theorem for all natural numbers, right? It's like, wow. Okay, so it's about an. We've already done this to an extent, right? We've seen it done a few times, right? If A divides B, and if D divides A and D divides B, D divides A minus B. But in some sense, this is pretty fancy, right? He proved that this formula works no matter what n you put in. Okay, so he proved a statement like this: for all n in the natural numbers, this infinity of objects, this statement P of n is true. Okay, so how do you do such a thing? So what you do is you start with the bottom. You start somewhere at 0, perhaps, and you prove the statement for 0. And now you assume, just like I could always give you a bigger number, if I start anywhere, you can get the next number. Say I know this is true at this place. I know this property holds at rung k of the ladder. And I show you whichever k it is, you can get to the next rung. Okay? That from knowing that this statement holds at P of k, I can use the fact that about what that means at P of k to prove that I can get to P of k plus 1. Okay? Then I've proven it for all integers. All right? If the statement is true at 0, then I say, well, it must be true at 1, because I know P of 0 is true, therefore P of 1 is true. If I know it's true at 1, I know it's true at 2, because I know I have a proof that P of 1 implies P of 2. And in fact, I have a proof that P of n implies P of n plus 1. So it implies that the statement holds for all integers. Okay? Yeah. Is there a question? Yeah. No, there's a different letter in here, right? This is assuming P of k, and this is assuming P of k plus 1. So it's slightly different, right? It's a different statement if the number changes. So I'm not assuming what I'm proving, right? Not yet. Yeah, but I'm not using P of k to prove P of k. I'm using P of k to prove P of k plus 1. And then I'm just using this property of the integers, nothing else. I mean, in some sense, what's really hard here is the integers. Like, why is there this thing? Why is this infinity of thing that goes on forever? That's really the power. Okay. So I mean, everybody seems to be happy with the natural numbers, not the integers, the natural numbers. Okay, so we have this statement. Let's see what Gauss did as a child. I mean, who cares? Anybody could prove this. But what he did was more amazing in his lifetime. But is this true? Is the formula true for 0? What is P of a number here? What you do is you plug in the whatever variable you have for n, and here the variable is 0. So the expression on the left is 0. The expression on the right is 0 times 0 plus 1 over 2. Yeah. Okay, so now for all k greater than 0, we want to say that P of k implies P of k plus 1. So we call this P of k the induction hypothesis. It's just language that we use when we're doing induction proofs. So we have that P of k is this whole statement. I should have used 3 equal signs in quotes, but it's that 1 plus 2 up to k is equal to k times k plus 1 over 2. I'm just plugging in k. Okay? Okay, so now what I want to prove is a statement about the sum of the first k plus 1 in natural numbers. I suppose I should have 0, but it doesn't matter. Okay? Does that make sense? Okay. What I can do is I can look at this sum from 1 to k, and I know I can use my induction hypothesis here. I could use that statement anywhere I want in my proof. So I'm going to use it here. I see 1 through k. I know it's equal to k times k plus 1 over 2 by the induction hypothesis. Okay? So that's why they're all in red, right? I'm just plugging into the induction hypothesis. Okay, so now I'm doing algebra. I think this is algebra, right? Getting a common denominator. I multiply the k plus 1 times 2 to 2 over 2. And then I collect up the terms. What can I do now? I can factor, right? And so you get this. That's P of k plus 1, right? So if you look at it, what I do here, P of k plus 1, the expression says that the sum from 1 to k plus 1 should equal k plus 1 times k plus 2 over 2, which is exactly what I proved. Okay, so I started with the property for k, and I know the property now holds for k plus 1. I didn't assume anything in particular about which k I used. It works at any natural number, so it says I can keep going up the ladder forever. And this is hard. People don't like it. It's like, what? But you should be okay because you know about the natural numbers. You know they go on forever. And that's really the magic here. Okay? Okay, so then it's the principle of induction. Okay? Are there questions? Okay, so the notes sort of visualize it as this. You know if the one domino drops, your first one drops, what's going to happen to all of them? Are you confident that they're all going to drop? Why are you confident? You can look somewhere in the middle of this sequence and you can see, oh, if this one drops, the next one drops. So they must all drop eventually. Okay. So for all k, if this one drops, the next one drops, right? If the k domino falls, it implies that the k plus first falls, and so on. Okay, so the infinite ladder, again, now instead of the integers, we're just saying, if I know p of 0 is true, and I know that p of k implies p of k plus 1, I can plug in 0, and I say, oh, okay, well, I can just plug in, for all k that's true, I plug in 0 there, that tells me p of 1 is true. And now I could use that statement again to get p of 2, right? I'm just plugging in 1 into that for all statement, and I get p of 2. And I can do p of 3, and so on, right? And this is the way the integers work. And it goes on. Yeah, it's your favorite example of of infinity. Okay, so let's try this again. And there's more. Let's just slightly just to review. Now that I just really want you to understand, believe in induction, because even now I'm like, oh, induction. Sometimes I'm like, because you're writing down a proof for an infinity of proofs in some sense. We did it before when we said a minus b is divisible by d, but this is another sort of, the building up is sort of very nice. Okay? So assume the predicate p of n for n equals k. P of k is this statement. P of n is true for n equals k plus 1. That's what we're asking. We're proving p of k, right? And then we're plugging in k plus 1 into the expression n. Now I use different variables here, k, to indicate going up, just to make it clear. Okay? So the sum of the first k plus 1 numbers is the sum of the first k plus k plus 1. Now this blue statement, all the blue things here, the blue things in the equation, is the induction hypothesis. It's a sum from I equals 1 to k of I is equal to this thing on the right-hand side. And then the rest of it is the same. Okay? Okay, so the same argument works. It didn't matter what k I started with. Okay? So the induction step was that p of k implied pk plus 1. Is this a proof? Again, it shows you can always move to the next step. Okay. Yeah. So, and so on, right? Let's see what, I just want to see something. Okay. Okay, so now, here again, you can think of it again. This is just climbing the ladder. You start at p of 0, you can go, no, you could get the next step, you get p of 1. now you have P of 1 to work with. So you have P of 1, right? You have the antecedent of this implication. P of 1 implies P of 2. You get P of 2. And so on. It just keeps going. Okay? Yeah. I'm not. I'm assuming the statement is true for K. I'm proving it for K plus 1. No, I'm saying P of K implies P of K plus 1. N doesn't need to be there. N equals K plus 1. That's just the statement again to say what does P of K plus 1 mean? Okay, P of N is a free variable, right? P of N there's a free variable N in the predicate. He's just getting there's some, you got to be careful when you set up your predicate. What is the predicate here? Does everybody see what the predicate here is? It's what is the free variable in the sum from I equals 1 to N of I equals of I? It's N. Okay? So now I could plug in for that free variable, I could plug in K, and then I could plug in K plus 1. And I want to prove, then they're different statements now. P of K is a different statement than P of K plus 1. Okay, P of K says K, this thing equals K times K plus 1 over 2, and so on. Okay. Please be still, because some people want to listen to the end. So please be still until the end. Thanks. If you need to go early, that's fine, but try to do it very quietly. So, okay, sounds good. Okay, the predicate P of N is true for all natural numbers. So I'm sorry to belabor the point, but you just lose your confidence sometimes when you're doing induction, because it's so powerful. Okay, you just have to prove this little thing, and then it seems to work in a huge context. Okay, so for natural numbers, you can prove this. Later, we'll prove, next lecture, I'll prove different statements. The sum of the first n odd integers is a perfect square. Here's where the thing that was powerful here is P of n is already a big statement. As you get bigger, the statement is talking about adding up a lot of things. So the statement is already sort of quantified and getting larger and larger as a statement. Okay? But, we proved something for all the natural numbers before, but it's really useful to build from the fact that it's true for one smaller natural number, right? It was really useful for Gauss to know that the formula worked for 1 through k to then derive the formula for the next one. So it's just a very powerful way to reason from and build up to an infinite set of objects. Okay? And again, this is a basic form, and you will do it a lot. Okay? So we'll see you next time. So.
Can we say that when we were proving that the root of 2 is not a rational number, can we say that because the rational number is divided, it's the definition of rational number is like a divided by b, and a and b are both, like, they only have one as their roots.
What are you saying? I'm sorry.
When we are proving this,
What's the theorem saying?